Hi guys, and welcome to another video in organic chemistry. Today's video is going to be on hybridization and Lewis structures. So hybridization is a concept that most general chemistry students are introduced to because it's an important concept to understand how atoms are using their electrons to bond with other atoms. Now, in organic chemistry, it's not as important, but typically on an organic chemistry exam or quiz, you will need to be able to identify the types of orbitals that are being used for bonding versus the types of orbitals that are being used for lone pairs in any given molecule. And so in organic chemistry, there's going to be typically three different types of hybridizations that can possibly happen. So one type of hybridization is known as sp hybridization. The second is known as sp2 hybridization. And the third is known as sp3 hybridization. So if we remember from general chemistry, hybridization is simply a mixing of atomic orbitals of the same elements. And because we're dealing with carbon, nitrogen, oxygen, our halogens, and hydrogen, the only orbitals we really care about for bonding are our s and our p orbitals. So remember that our s orbitals have a spherical shape or circular in 2 dimensions, and our p orbitals have this tear shape or dumbbell shape. And there are 3 p orbitals because there are ones that point in each direction in space: the z, the x, and the y. It's sort of arbitrary to choose what is x, what is y, and what is z, but typically the z is chosen in the vertical direction, x left to right, and our py points in and out of the board, which is a bit difficult to draw. But it points in and out of the screen. So this hybridization is basically essentially taking a combination of 2 or more of these orbitals to get new orbitals for bonding. So as the names indicate, s and p is a combination of one s orbital and one p orbital. We're just going to take the px for visualization purposes because it is much simpler to visualize. So when we combine one s orbital with our px orbital, which is shaped in this way, we can get 2 different combinations. So these orbitals are simply very complicated mathematical equations, and we can take these equations and we can either add them or subtract them. If we add them, the 2 orbitals will combine in what is known as a constructive manner, and if we subtract them, then that means that we will get a destructive combination of the s and the p orbitals. So because we are mixing 2 different orbitals in 2 different ways, it turns out that the number of orbitals that you mix together has to be equal to the number of orbitals that you get out from the mixing. Okay, this is just a conservation of orbitals, so you can't mix 2 orbitals and then come out with 3 or come out with 1. So we actually end up getting 2 sp orbitals when we mix an s and a p. And the only difference is that one is oriented to the left in such a way that it points left, and the other sp orbital points to the right, as such. And they sort of meet in the middle. So this little nub in the middle here, what the two sp orbitals actually look like individually is you have a little nub here and a big lobe pointing out in one direction. And so if you overlap the other sp orbital, the two little small nubs will overlap with each other, and each orbital is the sp. So this is the type of hybridization that can occur. With sp2, the difference is that now we're going to be adding an additional p orbital, either the py or the pz. Again, it really does not matter which one you choose. But the point is that when you mix an sp2, or when you mix s and p orbitals together to get sp2, we're going to end up with 3 sp2s. And the general shape of these sp2s, all combined together on a single atom, is going to look as such. So it'll look like a three-leaf clover, and each of these lobes is an sp2 orbital. And as you can imagine, we can do the same with sp3. So if we combine our s orbital and our 3 p orbitals, we're going to get something that in 3 dimensions is sort of very difficult to draw, but I'll try my best. You will get something that looks like this. And each of these lobes is an sp3 orbital, which can be used for bonding or for lone pairs, depending on the situation of the molecule or the element that is involved. Now, to determine the hybridization of any element in any given molecule, whether it's a simple molecule or a very complicated molecule, is actually a very simple process. So what we're going to need to do is, in order to determine the hybridization of an element, we're going to need to know 2 things. What we're going to do is we're going to calculate what is known as or what I call a hybridization number. And this number is very easy to calculate. Essentially what it's based on the number of atoms attached or bonded plus the number of lone pairs. Now this might seem familiar to you because this is exactly also the way in which we determine the geometries of molecules from VSEPR theory. So, because we're dealing with organic chemistry, this hybridization number is going to always be one of 3 numbers, either 2, 3, or 4. If the number you calculate comes out to be equal to 2, what that indicates is that the hybridization of that particular element is sp. If it comes out to 3, the hybridization is sp2, and if it comes out to 4, it is sp3. So some examples of molecules that are relatively simple. So carbon dioxide, water, ammonia, and of course we need to draw in the lone pairs for all of these in order to do this correctly. So if we determine the hybridization number for these molecules, hydrogens only use s orbitals, so hydrogens don't ever become hybridized. We're mostly going to focus on the elements oxygen, carbon, nitrogen, and our halogens. So here in this case, this oxygen has 2 atoms bonded plus 2 lone pairs, which gives us a hybridization number of 4. And therefore, because this hybridization number is 4, this oxygen is sp3 hybridized. If we do this for carbon dioxide, we will see that this carbon atom has 2 atoms bonded and 0 lone pairs. So its hybridization number is 2, which indicates that the carbon is sp hybridized. If we take one of the oxygens as an example, because the other oxygen is identical, this oxygen has 1 atom bonded and 2 lone pairs. So its hybridization number is equal to 3, which indicates that this oxygen is sp2 hybridized. Okay, and lastly, this nitrogen here, we have 3 atoms bonded and we have 1 lone pair, and so its hybridization number is going to be equal to 4, which means that this nitrogen has a hybridization of sp3. So now that we can determine hybridization number and determine hybridization for any element, what we can do with that information is we can get a much clearer picture of what is exactly going on in terms of the bonding and the orbitals used in a given molecule. Now, carbon dioxide is a very good example of this because it incorporates a lot of different features in a single molecule. So we've determined that each oxygen here is sp2 hybridized and the carbon in the middle is sp hybridized. So what does this mean? Well, we'll see here that we have a double bond, correct? So that means we have 2 bonds. Now, the bond at the top or the bond at the bottom, whichever one you want to sort of focus on, one of the 2 bonds is referred to as a sigma bond, or most commonly called a single bond. Now, orbital-wise, what is happening here is the carbon in the middle, because it's sp hybridized, it has 1 sp orbital pointing to the right and another sp orbital pointing to the left. This is our sp orbital here and another one here. The oxygen has sp2 orbitals that are being used. And if we remember the shape of sp2, it has this triangular shape where the orbitals are pointing in the direction of these lines like this. So if you can imagine, I purposely drew the lone pairs this way so that the oxygen has its sp2 orbitals pointing in that orientation. I'm going to use a different color here. So the oxygen in the middle, or on the right, has an sp2 orbital pointing directly to the left towards the carbon. The other sp2 orbital is pointing diagonally to the right, and the other sp2 orbital is pointing diagonally down. And these orbitals is where these electron pairs exist for the oxygen. And on the left-hand side, we have the exact same situation. The oxygen's sp2 orbital is pointing to the right, one to the upper left, and then one to the bottom as such. And so the lone pairs are also existing in those lobes. Now, this overlap that we see here between the sp and the sp2 of carbon and oxygen respectively, this is what we referred to as the sigma bond. And what technically defines this as a sigma bond is that the electron overlap, or the orbital overlap, is between the nuclei of the atoms. All right. So one nucleus of the carbon atom is here, the nucleus of the oxygen is here, and the electrons are sandwiched in between those two nuclei. So whenever we have this case of electrons overlapping this way between the nuclei of atoms, this is what is referred to as a sigma bond. So now you must be wondering, well, aren't there other p orbitals that we haven't used? Because remember, we have 3 p orbitals. In the case of hybridization for sp, we've only used 1 out of the 2, or 1 out of the 3 rather. And in the case of sp2, we've only used 2 out of the 3. So what are those p orbitals doing? So we're going to get a picture of what the p orbitals are doing now. So to get a clearer picture, we're going to have to omit the sp2 orbitals for a minute to get a better look at what's happening with the p orbitals. So again, if we draw our Lewis structure for carbon dioxide, our carbon in the middle is sp, and our 2 oxygens are sp2. So now the carbon in the middle, because it has sp hybridization, that means that one of the p orbitals, the pz, which is pointing perpendicular up and down vertically, this is our pz orbital. And there's also an unhybridized p orbital that is pointing perpendicularly to this p orbital, going back and forth behind and in front of the screen. So this p orbital here is going this way, perpendicular to the blue one at 90 degrees. And this is our py orbital. So the pz, or the px orbital rather, is the px orbital that is hybridized as sp. The py and the pz orbitals are unhybridized. On the oxygen atom, we have as well one p orbital that is unhybridized. So for oxygen, the one on the right, in order to form a double bond, this oxygen has a p orbital that is parallel to the pz of our carbon. So this is another pz orbital for oxygen. And on the left, the oxygen has also an unhybridized p orbital, But the p orbital that the oxygen has on the left that is unhybridized has to be a py orbital. And the reason for this is because the overlap of p orbitals, rather than being sideways, have to be parallel to each other in order to overlap. So one overlap occurs between the pz orbitals of carbon and one of the oxygens, and the other overlap occurs between the py orbitals of carbon and oxygen. And this overlap of p orbitals sideways like this in a parallel fashion is known or referred to as pi bonding. The letter pi. This is pi bonding. And this happens, or this is called pi bonding, whenever the overlap of the electrons occurs above and below the axis connecting the nuclei. So the carbon here has its nucleus here, the oxygen there, and the other oxygen on the left there. Because the line of the nucleus that connects the three together is straight across, the overlap of the blue p orbitals is above this plane, and so this is why it's considered pi bonding. And the red is the same. It's behind and in front of, but it's still above and below the axis of the internuclear connection. So this concludes the video on hybridization and sigma and pi bonding, how to identify hybridization in a molecule, and how to identify the type of bonding that is occurring in any given molecule between elements. Hit that like and subscribe button for more videos on organic chemistry like this one.